It's not square planar, it's a square pyramid. So with the octahedral geometry, whoops, back up. With the octahedral geometry, the angles are going to be 90 degrees, and it's going to be a square pyramid. So square, pardon my abbreviation, pyramid. In other words, the top is the top of your pyramid, and the base of that pyramid is a square. So square pyramid based on 5 bonds and 1 lone pair that has to be in this case. The angle should be 90-degree angles. The geometry around the central atom here is called a square pyramid. All right, second example, B. Here we have 3 atoms, so 3 bonds attached to a central atom, and if there was nothing else present, you would expect to have an angle that looks like 120-degree trigonal planar geometry, but we don't. This is something else. We apparently have to have another a non-bonding pair, a lone pair of electrons there. And so 1 lone pair means that there must be 4 electron clouds. And the result is tetrahedral electron cloud geometry, but we have a lone pair present, so instead this is what we call trigonal pyramid, trigonal pyramidal for the geometry. The bond angles are based on tetrahedral electron charge clouds when there's 4 total charge clouds, so the bond angle is somewhere in the vicinity of 109 in this case. It will be distorted because of a lone pair, but we're not going to be particular about the actual amount of distortion. The third example has 4 bonds around the central atom, and if there's 4 bonds and there's nothing else present, it should be tetrahedral. Well, that diagram does not look tetrahedral, it looks flat. And so there must be something else influencing the arrangement of these electrons, or the atoms, around the central atom. And so the only way I can see this makes sense is if you have 2 lone pairs, because it kind of looks like an X from the top-down view, if you will. And so there's got to be 2 lone pairs in addition to the 4 bonds for the octahedral geometry of the electron clouds. But when it's not 6 bonds, we have 2 lone pairs present. Now we have what's called square planar, because they're all flat in one plane. What results, what is in view of those atoms for the molecule, and the geometry there is going to be 90-degree angles. That's what you always get when there's 6 charge clouds. It should be 90-degree angles. There could be some distortion, but in this case it should be pretty symmetrical because the 2 lone pairs are as far apart from each other as possible, resulting in a fairly symmetrical looking arrangement. All right, example D. We have now 3 bonds around the central atom, and if there were no lone pairs present, we should expect to see trigonal planar geometry. Well, apparently this diagram looks like that. There doesn't appear to be any lone pairs, and so it should be just plain trigonal planar. When there's trigonal planar geometry, the bond angles in the compound should be 120 degrees. Next examples. What's the geometry around the central atom in each of these molecular models? All right. Well, on the left one, we have a central atom with 4 yellow things attached, and if that would be 4 bonds. And on the right, we have a central atom with also 4 bonds, but they don't look the same. You have to remember that these are attempted to be drawn with representing actual geometry, and so you have to take the artistic angles into account. And the one on the left doesn't have the same angles. It looks as the one on the right. So the ones on the left appears to be the geometry where there are 4 things around the central atom without lone pairs. So this should be tetrahedral geometry for the molecule, 109-degree angles. 109 and a fraction, but that's close enough. 109-ish degree angles for tetrahedral molecular geometry. Lacking any lone pairs, the electron cloud geometry is exactly the same as the molecular geometry. Okay, the one on the right can't have only bonds. It must also have some lone pairs because it doesn't appear to be representing tetrahedral geometry. So how many lone pairs might there be if you end up with this arrangement? Well, it's either going to be 1 or 2. And if there were 2 lone pairs, that would give you a different geometry than we see here. So it would be the octahedral sort of thing with 2 lone pairs. In this case, it should just be 1 lone pair for a total of 5 charge clouds. and 5 charge clouds is what we call trigonal bipyramidal for the charge cloud geometry, but the molecular shape is not trigonal bipyramidal because we have a lone pair on that central atom. So instead, this is the funny one with the somewhat colloquial looking name. We call it seesaw geometry. And the bond angles are two different kinds. Between the two that are shown at the top here would be 120-degree angles, and between the top two and either of the horizontal bonds would be a 90-degree angle. Remembering that there's two kinds of angles in the trigonal bipyramidal electron cloud geometry. All right, so here's another interesting set of diagrams. See if they can make any sense. What's the geometry around the central atom in each of them? What kind of shape and angles? And there may be a hidden atom behind something in what's visible in each diagram. So the leftmost diagram, central atom with 5 things attached. Well, that would be 5 bonds on a central atom. Is there any suggestion of lone pairs here? I'd say not, because the bond angles appear to be consistent with the trigonal bipyramidal geometry. In other words, the angle between the top and the side here looks like 90 degrees. That's the way it appears to be represented. And between the top one and the one down at the bottom looks like the 120-degree angle. And so we call this our trigonal bipyramidal molecular shape. Lacking lone pairs, the molecular shape is the same as the electron charge cloud geometry. The center diagram of this set you can view has bond angles that would appear to be 120 degrees. Those 3 around the periphery of the red circle appear to be distributed equally, so that would be 120-degree angles 3 places. But there's one other atom shown here, and that one other atom would have to be coming straight toward you from the diagram, and the angle between that and its neighbors would have to be the 90-degree angle coming straight away from the plane of the paper or the plane of the diagram where the 120-degree angles are. Again, this is trigonal bipyramidal kind of geometry. In order for that to be the case, we certainly can see 4 bonds. Is there a 5th bond present? There could be one hidden behind the central atom. If there were a lone pair, it would end up being in the equatorial position. And so in this case, it's a total of 5 bonds. It's the same as the left molecule, just turned so that you can't see the 5th atom. So these two are essentially the same compound, just turned from a different angle. If there were a lone pair, it would be on the peripheral or the equatorial position in these kinds of things, and you get seesaw geometry, which would not be the same as what we see here. The third diagram has apparently 4 bonds, again, to a central atom, sure enough. But this time we have to decide if there's more things attached that we can't see. Well, if you have the bond angles that we see here, this looks like 90 degrees, right? And the same on the opposite side. And again, would be also 90 degrees to the atom that comes straight away from the plane of the diagram in the middle of the red circle. So you got all 90-degree angles, and the only way you're going to have 4 bonds and all 90-degree angles is going to be if there's 2 lone pairs. So 2 lone pairs for a total of 6 electron charge clouds. 6 electron charge clouds with 2 lone pairs is what we call what this looks like, and namely that of a T-shape. Not real sneaky, but something you got to figure out when you look at it. T-shape. So 3 different ways to see 4 things attached to a central atom. They're not all the same thing. A couple more examples. These molecules, 3 of these have a tetrahedral central atom and 1 does not, and which one does not, and how can you tell? There sometimes would be the possibility they've hidden an atom behind the central atom in the diagram. All right, what do you think? Well, the first one, you have to look at each of them and kind of interpret the angles. The angle between the center and 2 peripheral atoms here, to me, looks like the 109-degree angle. So that would be, in fact, our tetrahedral geometry. The same thing would be true on the second one. That doesn't look like 120-degree angles. Again, I believe that's the 109. There is nothing hidden, and there's shading that represents the fact that these three peripheral atoms that are shown around the center black one are pushed away from the plane of the diagram. The third one instead has a very planar arrangement, and that one will not be tetrahedral. This would be the square planar arrangement that you get with 4 bonds and 2 lone pairs with 90-degree angles, and that would not be tetrahedral. So square planar at 90-degree angles. And then the third one then must be, the last one, sorry, is apparently going to be also tetrahedral, because it says there's 3. 3 out of them should have the tetrahedral. Well, how can that be? Only if there's another atom hiding back behind the black central atom, then that would be consistent with tetrahedral geometry. Again, this, if you're looking at it carefully, should look like a 109-degree angle more than something else. All right, one more set of examples, or one more example. We have bromine pentafluoride, molecule whose name is hard to spell, but let's discuss the geometry. So what in the world do we expect for the shape of the molecule? Well, the central atom has 5 fluorines attached, so we have 5 bonds. And when you've counted up the valence electrons, it becomes evident that there has to be also a lone pair on the bromine. And so 1 lone pair plus 5 bonds gives us a total of 6 charge clouds, electron charge cloud. And whenever that occurs, the electron pair geometry, or the VSEPR, the repulsion of those electron clouds pushing each other as far apart as possible, means that you have octahedral electron cloud geometry. However, that's only the electron charge clouds, because there's not, the whole molecular shape is based on the fact that there's also a lone pair pushing these things into the geometry that they do exhibit. And so instead of having octahedral, we'll have to have 4 atoms in a plane plus 1 that sticks up perpendicular from them, because all the bond angles are 90 degrees. And so when that's the case, we have what's called the square pyramid. So if you go back to your chart, that would be the example of 5 bonds and 1 lone pair to give you the square pyramid, and all the bond angles are 90 degrees. The more practice, the better. The more times you do these, the more sense they make. Good luck with these in various examples, and I hope this helps you. See you in class.